for coming to the workshop today. As you know, this is a workshop about rapid prototyping antennas, particularly cute antennas, which is awesome. Kristen has, their background is primarily in RF engineering with a PhD in electrical engineering as well. And yeah, so this is mostly just going to be learning about the basics about antennas and how to rapidly prototype your own.
Hi, everybody. I'm Kristen. Glad to have you here. What you want to think about if you're going to make an antenna is, first, what's your application? What are you using it for? Is it Wi-Fi? Is it a garage door opener? And that will tell you what frequency you need. The frequency will inform what the geometry, what size you need. So you can see here, the transmission is coming in from the left. And so there's the width of the antenna. Of course, I have this sort of sideways, sorry about that. The width and the length. And that's on top of a substrate, anything will do. And if you'd like to look at my demos, I can pass them around while I'm talking. These are ones I've made and annotated. So a tiny bit of math, because what would a hardware conference be without math? So the size of the patch, a rectangular patch, is going to be half a wavelength. And you're not going to need to worry about this. I'm just going through it. There's no quiz later. Sorry, serious students. All right. So C, the speed of light equals the frequency times the wavelength. And you use that to get your width. And if you just follow this calculation, you get 61 millimeters for the width of this antenna. But wait, there's one more thing we haven't taken into consideration, and that is the material itself. So you've got some material in here, and you've got electric field in between here underneath this patch, between this patch and the ground plane on the back. And that's not seeing air or vacuum, that's seeing this chipboard. So you have to take that into consideration because it's going to change the wavelength, and therefore it's going to change the size of the antenna you need to make. So by a little bit of trial and error and different size sort of standard patches, I figured out that the dielectric constant of this chipboard is about 2.1. And so that's great. But there's one more step. Since half of your antenna underneath is seeing the chipboard, but the other half on top is seeing the air, you have to sort of not quite average them out, but you have to take both of those materials into consideration. And that is the effective dielectric constant, which is about 1.8. Unfortunately, there are online calculators to help you with those. So you don't have to worry about doing the math yourself because that gets a little complicated. Okay, so for 2.45 gigahertz, you want a square that's about 50 millimeters wide and 42 millimeters tall or long. And you can have a little microstrip of feed on here if you like, as you can see here, or you can just put the square right down at the bottom where we're going to put the connector. So here's our workflow for today. And I think I have a few more things to talk about. Yeah, no, that's okay. So we're going to pick a frequency. I think it's probably easier if you want to pick Wi-Fi, Bluetooth, 2.45. If you really want to do 5 gigahertz Wi-Fi, just cut everything in half. Make it twice as small because it's twice the frequency. So half the wavelength, so just make it smaller. Okay, we're going to design and cut out our antennas. We've got some templates floating around that are based on the test antennas that I've made that I'm passing around. You can cut out any of these and sort of copy that onto your copper tape, or you can start making your own. There's enough supplies for everyone to do 2 antennas. So I figured if you'd like to, you can do 2 template antennas. You can do 1 from the template and 1 from your own imagination. You can do 2 from your own imagination. So you design and cut out. We'll test up here at our testing station, and Darcy and I will be up there to help you out and explain what's going on. You've got, on the right side is a vector network analyzer that's connected to my computer, and that will test the reflection of your antenna. So hopefully there's going to be a part where your antenna stops reflecting and starts transmitting, and that's going to make a big dip. And that's the happy place of the antenna. That's its best operating point. So you'll be able to see if your frequency is right on the money, if it's a little off. And anything below about minus 10 dB, rule of thumb, is pretty good. That'll work. And so we test if you want to iterate, if you want to make the same thing. If you ended up with the frequency a little too high or too low, you can change the size, make it a little bigger, a little smaller. And that should get you, right on the money.
So if you cut it too small,
Mm-hmm.
can you build taping a little bit piece around there? Like,
Yep.
that like.
Yes, you can. You can extend it by adding more tape around the edge.
Right.
Sure.
So at what point does the material have to be like? This is where like antenna theory. Like, like if you have, you're making a yagi and you make all these different parts. Like, well, how does physics do those at the same device? This is my question. It's reflected because it's a core light. But it's really
Because they're touching, so they're all electrically connected. And it's sort of, okay, so what he's talking about, I'll let you get started and then I'll answer your question.
Sure.
And for everybody else who wants to know what a yagi is and how that works. Okay, so this is the LibreVNA is up there. I also have an RF Explorer. I don't have it out, but I can get it out, and that analyzes the RF spectrum. You can attach your antenna to that and see what you're picking up from the Wi-Fi channels around, if you'd like. Here's some general resources. I also have an LED over there that's connected to a Bluetooth circuit, and you're going to connect your antenna to that circuit, and you can use my phone to change the color of the LED just to test a yes/no. Does my antenna work for what I need it to, or does it not work? And so I guess I didn't really write out an instruction page, but what you're going to do is you've got some 3-inch squares of chipboard here, and you've got some copper tape, and you're going to take some of your copper tape and cut it into a 3-inch square to be the back. That's going to be your ground plane like you can see each antenna has a ground plane on the back. And then you're going to take your next 3-inch square and you're going to cut your favorite shape out of it. And then when you stick it on here, you're going to stick it so the bottom of the shape is just touching the bottom of this chipboard, but it's not wrapping around. You don't want your front and your back to be touching. So don't wrap it around the edge. The edge is bare. And then after you've done that, you're going to take this little connector guy here. This is an SMA connector for a PCB edge. And it just barely fits. So it's a press fit sort of thing. So you just take it and you kind of slide it on carefully so you don't scrunch up the tape. The tape is about 0.6 millimeters, I think. So it's quite fragile. And I have more up here. If you mess up a piece, don't worry about it. Come get another square. By basically doing it and figuring out.
Oh, that one is a good dip. Yeah.
That's a good tip. That's a 2.67 minus 37. It's great.
I'm right behind you. What is
So the
the
frequency
significance of the minus? Yeah.
minus is how much it's losing. So if it's 0, it's not losing anything. It's reflecting everything. If it's minus, it's losing some to the being transmitted.
Yeah.
It works.
We shaved it down a little bit to get to the right frequency, and it looks like it's good enough.
That's pretty.
It's so exciting.
It's so cool.
I keep moving it, and it likes to.
Yeah. Yeah, exactly.
Thank you.
So you said the more minus, the more it's losing. That's good, right?
So it's good because you're not losing it.
Everything. Okay, gotcha.
You don't want to keep any of the energy.
Oh, wow. Right there. 2.35. That's very close. That's good.
Very cool.
Stuck it.
I want to see it like it. Yeah, I'm gonna watch that because I'm really interested.
The duck antenna.
Is that because we're in Oregon? Oh, look at that.
What is that?
So this one is 2.35, and that's pretty close to where you want it to be.
And it seems to be doing well in the
It's doing
3.
very well in the 3.1.
Gotcha.
So it's a little high. I would have made a little bit bigger gun.
Gotcha.
Actually, a good Wi-Fi antenna. Nice.
I was also thinking to make a one without being too long.
2.2 is going to be about twice the size of 2.4. Yeah. Oh, so. But if you want to tape together, I've got some extra chipboards. Yeah. Tape together 2 or 4 strips.
How do you,
No, go for it. Go
oh,
for it.
wow, it'd be exactly half of that.
Yep.
Ooh, this one's interesting.
Yeah, I was hoping it could be a much lower frequency, but instead it just made a mess.
That's a lot of frequency bands going on there.
None of them what I wanted. That part B of the experiment. Wow. That's a huge impact.
No, it's peeled off.
Oh, yeah.
What are you aiming for?
Way lower than that. Yeah, so I mean, yeah, it's just highlights that I don't know what I'm doing.
Six says a lot of us don't.
What did it do, Jeff?
Well, 3 gigahertz. 3 gigahertz, which doesn't
interesting.
make a lot of sense to me. But